Hello, I'm Meg Martin, and I'm going to be discussing magnetic sensors. Magnetic sensors relate closely to the topics discussed in ECE 303 and also have many different real-world applications. From gaming consoles and smartphones to automatic toilet and laundry machines, magnetic sensors are almost everywhere. There are many different types of magnetic sensors, but we will discuss three: coiled sensors, reed switches, and Hall sensors. For each of these, I'll describe how they work and their applications. Coiled sensors have a wide variety of uses: magnetic storage devices such as magnetic tape or a hard disk, induction heating, radio antennas, stereos, record players, and metal detectors. Coiled sensors are fairly durable due to their shape, but are only able to detect time-varying signals, so a still signal or one that is moving too slow may not be detected. In class, we discussed ways to generate electromotive forces. They require a moving loop, B field, or both in order to be generated. We discussed Faraday's law in class, which equates the curl of the E field to the time derivative of the B field. From Faraday's law, we are able to find that the V EMF equals the time derivative of the integral of the B field over a surface. The image on the slide gives a visual representation of this. You can see that as the magnet moves towards the coil, a downward current is induced and vice versa. Note the negative sign in the derived equation as you visualize this. I will describe how this process happens with a metal detector. As the detector passes over a piece of metal, a time-varying B field is induced in the sensor. The coil then produces a voltage, which produces a beeping sound. Always remember, coiled sensors must have a time-varying component. Now let's look at reed switches. Reed switches have a plethora of applications in security systems, household appliances, automobiles, robotics, and automation. Reed switches, in spite of their glass casing, are extremely durable and tolerate many harsh environments. They operate across wide ranges of temperatures and humidities and can tolerate 30 Gs of shock. In addition, they require no power when in the off position. Reed switches operate based on an external magnetic field. When an external magnetic field is present, the reeds become magnetized. The internal portion of the reeds are attracted together to create an electrical connection. Keep in mind that this is a switch with only an on and off position. Hall sensors are probably the most complex of the sensors discussed in this presentation. Hall sensors are used to detect seatbelt position, balance washing machines, in automatic sinks, toilets, and hand dryers, as well as in many other applications. A key feature of Hall sensors is their ability to function when the B field is constant. Hall sensors work based on a principle called the Hall effect. The Hall effect stems from the equation for magnetic force and Lorenz's law. You can see these equations on the slide. However, the hand rule in the visual may be more useful for interpretation. Essentially what happens is a magnetic flux is applied to a semiconductor surface and a current is supplied across it as well. The current is what allows this sensor to be effective even without a time-varying B field. Due to the magnetic flux and moving electrons, a voltage is induced. Keep in mind that the induced voltage, B field, and current will all be orthogonal. I hope you see that there are many different applications of magnetic sensors and that the fundamental concepts behind the magnetic sensors that allow them to operate tie in with the concepts learned in ECE 303. Coil and Hall sensors both utilize major topics covered in the class, Faraday's law and Lorenz's force, and provide practical applications to the concepts we learned. Each type of sensor we discuss provides unique capabilities to consider when designing a product. If you have any questions or comments, concerns, if you want to know anything more about magnetic sensors, feel free to reach out to me. My name again is Meg Martin, and my email is mkmarti4@ncsu. Thank you guys so much for listening.